Okay, today we are going to continue the study of the rigid bodies, and we are going to talk about the angular momentum of these rigid bodies, how to express the angular momentum in terms of the inertia tensor that we have been dealing with in previous videos. So just let me remind you what is the main idea. And remember that we have a rigid body, and well, we can define a coordinate system like this, x, y, that will help us to locate a point, a particular point on the rigid body. Okay, and we can also define a different coordinate system that will be fixed to the rigid body, like this. For example, let's say that it is with the coordinate x prime and y prime, and remember that during the motion of the rigid body, well, this coordinate system will stay with the rigid body. That is what it means to be fixed. Okay, so that means that the components of the vector that locates that point, well, are going to be constant because the coordinate system is moving with the rigid body. Okay, so this is something that we have been watching in previous videos, and for example, in the video of the inertia tensor of the rigid body, we showed some relations that are going to be very useful in this video. So for example, the first relation is the one that relates the components of this vector, that is the vector of position r for the particle alpha. Well, the equation that relates the components for this vector in the natural coordinate system and the prime coordinate system is that the j component of this vector is equal to a j q prime x q prime alpha, where this is the component in the prime basis, the one that is fixed to the rigid body, and this is the component on the natural coordinate system that is well, an inertial frame that is staying at the same point. It is not moving during the motion of the rigid body, and these a's, well, they represent the elements of the transformation matrix that relates the two orthonormal bases corresponding to each coordinate system. Okay, another relation that we showed on previous lessons is that a dot ki prime is equal to the Levi-Civita tensor ijs omega s akj prime, like this. Remember that in order to find the inertia tensor, we needed to find, well, the kinetic energy, and the kinetic energy of the rigid body, well, involves what is the velocity of the rigid body. So that's why we needed to calculate the derivative with respect to time of this, and that generated these derivatives with respect to time of the components of the elements of the matrix. Okay, actually, another relation that we found that is immediately from this equation is that x dot k alpha is equal to aki prime dot xi prime alpha. Look that taking the derivative of this is equivalent to just take the derivative of this component, because again, this component that is in the prime basis, it doesn't change on time. Okay, so it's like a constant, so the derivative of this with respect to time is just the derivative of this with respect to time times this. Okay, perfect. Another relation that we are going to use that is very easy, well, we showed that on the first video of rigid bodies, is that the Kronecker delta IP is equal to AIR prime APR prime. Okay, this is also going to be useful. Perfect. And well, for now, the last relation that we are going to use is one that we haven't used yet, but just let me explain quick what is it about. We are going to have that the Levi-Civita tensor ijk is going to multiply BIP, BJQ, and BKR, and this is going to be equal to the determinant of some matrix B. Of course, these B's correspond to elements of that matrix B that I'm writing here, and this is going to multiply the Levi-Civita tensor but with the indices P, Q, R. Okay, perfect. Remember that, well, here we are only working with matrices 3 by 3. So for example, if you have a matrix 3 by 3, remember that taking the determinant of this matrix is multiplying elements that are from different rows and different columns. Okay, so that means that if you examine this expression, you will see that, well, I, J, and K cannot be the same. That are the indices that represent the row of each element. Okay, but they cannot be the same because this Levi-Civita tensor is telling us that if J is equal to I, then you know that the Levi-Civita tensor is equal to 0. So that means that every term here that corresponds to the same rows, well, they are going to be equal to 0. And it happens the same thing here. We have a PQR that correspond to PQR here that represent the columns of the matrix B. So that means that these Levi-Civita tensors are making that this product will only be valid for elements that are from different rows and different columns. And that is exactly what the determinant means. So that's why we have the determinant of B here. In this case, this is B, of course. So, of course, this is not a rigorous demonstration of this formula. It's just like a quick overview to understand what this formula means. And looking that we have been working with orthogonal matrices, well, we know that for an orthogonal matrix, B to the T is equal to B inverse. So if we take the determinant of BTB, well, this is going to be equal to the determinant of B inverse B, which is of course the determinant of the identity matrix, which is of course equal to 1. Okay, but from here we can say that this is equal to the determinant of B transpose times the determinant of B, which is equal to, looking at B is orthogonal, the determinant of B times the determinant of B. Of course, this is equal to the determinant of B squared. So we get that 1 is equal to the determinant of B squared, which means that the determinant of B is equal to plus minus 1. But looking at, of course, B represents a rotation matrix. You know that, well, for this kind of matrices, we take the determinant to be equal to plus 1. Because in other way, well, the matrix B will imply an invert of orientation, but we are not interested in those cases here. So we can say that the determinant of B is going to be equal to 1. So later on we'll see that we are going to use this formula with the determinant equal to 1. Perfect. So after saying this, let me remark what are the equations that we are going to use. We are going to start studying the angular momentum of the rigid body. Okay? Well, you know that the angular momentum is the cross product between the position vector and the linear momentum vector. So that is represented by this equation over here. We have m r cross r dot. So you know that there is a way to represent the angular momentum in terms of the index notation using the Levi-Civita tensor. So that is a very famous formula that says that the I component of the angular momentum can be seen as, and in this case for each particle of the rigid body, we will have the sum from alpha equals to 1 up to n of the mass times the Levi-Civita ijk xj times xk dot alpha. Okay, we are using the famous formula for the angular momentum in terms of the Levi-Civita symbol. Look that here we have the components of the r vector in terms of the basis of the original coordinate system in the inertial frame. Okay, these are the components in terms of this coordinate system that we have here. Okay, so we are interested in changing this to the other coordinate system, the prime coordinate system. And here we have a component for the velocity and here for the position. Okay, so this is like taking the angular momentum of one particle and then to the other particle and then up to the n particles that compose the rigid body. Then we sum all those components of angular momentum to get the total angular momentum in the I component for the whole rigid body. Okay, so after saying this, well, like I said, we are going to be interested in changing the basis of this component of the angular momentum, and we are going to use these formulas over here. We know that for the inertial frame we have this relation, so we are going to use this. And well, let me write it again. We have that xk dot alpha is going to be equal to a k I prime dot xi prime alpha. And as we mentioned, we had that this a dot is equal to this. So that means that we can rewrite this expression as the Levi-Civita ijs omega s a k j xi prime alpha. Notice that in this case we no longer have the derivative with respect to time for an element of a, and that this component is for the prime basis that is fixed to the rigid body again. Okay, perfect. So we can substitute this into this equation, and we have also that this component in the inertial frame basis can be expressed as, well, xj alpha equals to ajq prime xq prime alpha. So we are going to substitute this into here. Okay, so we are going to get that Li is equal to the sum from alpha equals to 1 up to n of the mass times the Levi-Civita ijk xj, which is going to be ajq prime xq prime alpha, and then xk dot, which is going to be the Levi-Civita ijs omega s a k j xi prime alpha. And actually this k is not primed. Okay, yeah, because remember that we are transforming from a base to another one. Okay, so that is why we do not have to use the prime notation in the k index. Okay, perfect. Let's see what happens with the Levi-Civita ijk ajq prime akj prime like this. Well, we know that this can be seen as a Kronecker delta IP EPJK. We are just switching the index of the Levi-Civita for a P, and to multiply it with a Kronecker delta, well, this is equal to the Levi-Civita ijk. So I'm not changing anything at all. I'm just introducing this Kronecker delta. So this multiplies AJQ prime, AKJ prime. Okay, so now, well, we can see this as an element AIR prime, APR prime. Okay, this Kronecker delta corresponds to this product over here. Then the Levi-Civita PJK, AJQ prime, AKJ prime. Okay, so let me rewrite this as AIR prime, Levi-Civita PJK, APR prime, AJQ prime, AKJ prime, like this. Okay, so now notice that we have a triple product of elements of a matrix A multiplying a Levi-Civita PJK. Okay, so it is very similar to what we have been talking about of this relation, like this. So again, looking that A is an orthogonal matrix, we are going to take the determinant of A equals to 1. So that means that the product that we have, we can express it as only a Levi-Civita symbol, but with the other indices. Okay, so that means that this can be seen as AIR prime, the Levi-Civita symbol, but now instead of PJK, it will be RQJ, and these are prime, of course. Here it's important to notice that J is different from J prime, okay? So just for not to get confused. Okay, so we had that this product over here times this is equal to this. So we are going to substitute this result into the angular momentum formula that we found. Okay, so we are going to get that Li is equal to the sum from alpha equals to 1 up to n of the mass AIR prime, the Levi-Civita R prime, Q prime, J prime, that is this, then the Levi-Civita IJS omega s xq prime alpha xi prime alpha. Okay, well, another famous formula that I didn't mention at the beginning is that, well, you know that a product of Levi-Civita symbols can be expressed in terms of well, a sum of products of Kronecker deltas. Actually, well, it will be like this. This product of Levi-Civita symbols can be seen as the Kronecker delta R prime S prime, Kronecker delta Qi minus Kronecker delta R prime I prime, Kronecker delta Q prime S prime. Okay, so let me rewrite this equation in terms of this product of Kronecker deltas. Okay, perfect. This is what we get if we replace this product into the angular momentum component. So what we are going to do next is to take out this element of the sum, and we are going to get that Li is equal to AIR prime, the sum from alpha equals to 1 up to n of the mass alpha, and then let me write this omega s here, and then, well, let's examine what is going to happen with this product when it multiplies the Kronecker delta here and the Kronecker delta here. Well, let's examine that this Kronecker delta is going to change this Q index of this coordinate to an I. So we are going to get xi times xi. And we have been watching in other videos that represents the magnitude squared of the R vector. So that means that we can write that this is the Kronecker delta R prime S prime times, again, this is xi prime alpha, but this is R squared. Okay, so we can write this as R squared. Of course, this is R alpha. and then minus, and let's see what happens with this other product of Kronecker deltas. Well, when we multiply this xq times this Kronecker delta is going to change this q to an s, and when we multiply this xi with this Kronecker delta, well, it will change this I to an R. So we are going to get xr prime alpha x s prime alpha, like this. And as you can immediately notice, we have an expression that is equal to the inertia tensor definition in the prime basis, in the fixed coordinate system. So that means that we can write this as, well, if I take this omega s here, you can immediately see that this expression is the inertia tensor r prime s prime. So that means that the Li component is equal to ai r prime, the inertia tensor r prime s prime, like this. So what we are doing is to calculating the angular momentum from the inertial frame, that is the natural coordinate system, in terms of the inertia tensor in the prime basis. And of course I forgot this omega s, very important, omega s prime. Okay, perfect. So this will be the final result of the lesson, which is very, very important. So if we define, for example, that this is the component of the angular momentum, let's say Lr prime, but of course in the prime basis, well, we can just say that the angular momentum is transformed just with this change of coordinates given by this equation over here. Remember again that this is the transformation matrix. So this is telling us that if we have the angular momentum in the prime basis, we just need to multiply by the transformation matrix, or an element of the transformation matrix, to get the angular momentum in the inertial frame, that is this one over here, the black one, the one that is not moving with the rigid body. Okay, that is very important. Perfect, so that is a good moment to finish this lesson.